Welcome to Control 4 Centralized Lighting. This course has 6 modules: Dimming Technologies, Transformers and Load Types, Centralized Lighting Hardware, Keypads and Wiring, Composer Design, and the Physical Installation. Module 1, Dimming Technologies. Before we jump into the course, let's learn some fundamentals about electrical basics. Electricity is similar to water. Water arrives under pressure from the source through your faucet, flows into the sink, and leaves without pressure through the drain. For electricity, hot wire coming from the panel carries full voltage, which flows into the sink, in this case the light bulb, and leaves without voltage through the neutral wire. When the circuit is closed, power now flows through the light bulb. You notice that the light bulb turns on and off repeatedly. As you change the frequency, you'll notice that the light bulb flashes more frequently. And when the circuit is opened, the light bulb turns back off. Dimming technologies. There are a few different dimming technologies. The first is phase-cut dimming. This dims a light bulb by switching the light on for only part of the sine wave. At 60 Hz, a light bulb is turning on and off 120 times per second. The light bulb turned off at the zero cross, where the sine wave hits the x-axis, and turned back on until the sine wave hit the x-axis again. Phase-cut dimming takes advantage of that fact. After passing the zero cross, instead of immediately reapplying power to the bulb, power can be withheld for part of the cycle. If power were applied halfway through the cycle, the light bulb would only be on 50% of the time, which is how you get 50% brightness. The flashing is still imperceptible to the human eye, but because 50% less light reaches the eye, it is perceived to be dimmer. Forward phase dimming leaves the light off at the zero cross, where the sine wave crosses the plane. And at 50% dimmed, the load receives power halfway through the cycle, again losing power at the zero cross, and regains power halfway through the next wave. Forward phase dimming is compatible with resistive and inductive loads. Reverse phase dimming is the opposite. Again, with an example at 50% dimmed, the load receives power immediately at the zero cross and loses power halfway through each cycle. Reverse phase dimming is compatible with resistive and capacitive loads. Adaptive phase dimming is capable of both forward and reverse phase dimming. It detects the load type screwed into the fixture and determines which phase dimming to use. Adaptive phase dimmers are compatible with inductive, resistive, and capacitive loads, making the adaptive phase dimmer virtually future-proof. The fundamentals of load limits. A dimmer's maximum load is based on heat generated from the dimmer itself. In a fully off position, a dimmer has full 120 or 240 or 277 flowing into it. Dimmers convert that energy into heat and expel it into the walls around them. There are strict regulations on the maximum amount of heat to be generated by a dimmer. A dimmer's maximum load is also based on electromagnetic interference. The dimmer's use cannot be detrimental to other electronic devices in the area. Control 4 dimmers are all tested and pass regulatory standards. A dimmer's minimum load is based on current leaked to the load. Dimmers by nature trickle power up to the load. Again, in a fully off position, a dimmer has 120 or 240 or 277 coming into it. Most of that energy is converted to heat and expelled into the walls around it. However, there's always a trickle of power that reaches the load. The minimum load is also determined by switch leg wiring. If the dimmer is wired without a neutral, then in order to power the dimmer, power must flow through the load as well. Too much power to the load may turn it on or flicker even in a fully off position. Another dimming technology is control signal dimming. Instead of the dimmer controlling the flow of power to the fixture, like phase-cut dimming, in control signal dimming, the fixture and dimmer are independently powered. Analog or digital signals are sent to a fixture's ballast or driver, usually used with fluorescent or LED lights. The ballast or driver interprets low-voltage commands and dims the load itself. Control signal dimming includes 0 to 10 volt dimming, high lume dimming, and dolly dimming. These are mostly used with fluorescent and LED bulbs. 0 to 10 volt dimming, also called 4-wire dimming, is commonly used with fluorescent lights and LEDs. The standard use allows for a 0-volt command for the minimum level. Each 1-volt increment increases the dimming by 10%. There are 4 separate standards for 0 to 10 volt dimming: 0 to 10, 1 to 10, 10 to 1, and 10 to 0, depending on the fixture. Generally, 0 to 10 volt dimming has no command for off. Instead, the circuit must be opened, generally through a relay, in order to cut power to the load. High lume is also known as 3-wire and is a Lutron proprietary standard. It uses 3 wires for control: a switched hot for the voltage on and off, a dimmed hot for forward phase dimming as a control signal, and then the neutral in order to complete the circuit. The Control 4 forward phase dimmer can be used with the high lume interface in Lutron installs. 0 to 10 volt dimming is very similar to high lume dimming. Generally, most fluorescent and LED fixtures have an option for either 0 to 10 volt or high lume. If high lume is spec'd out, it may be possible to get the lighting designer or the electrician to swap over to 0 to 10 volt dimming in order to take full use of the Control 4 system. Dolly DSI and other digital controls are not very common in North America, are generally more expensive than the other analog control systems previously discussed, and are most commonly used in large commercial projects. Currently, Control 4 has no way to control these lighting systems. DMX is another digital dimming standard, which is commonly used for theatrical lighting, high-end commercial, and LED lights, especially those that have control for color, direction, and shape. There is a Control 4 driver for DMX, but requires an additional hardware device to bridge between the two systems. Fundamentals on circuit breakers. When an electronic device turns on, there can be a spike of current to that electrical device. That spike is generally a large inrush many times higher than during normal operation. That spike can also damage electronics in dimmers and switches if it's not managed properly. Circuit breakers trip if that spike is too high, cutting power to the device to prevent any damage. Basic math for your circuit breakers: watts equals volts times amps. If you have a 15 amp circuit breaker at 120 volts, 15 times 120 is 1800 total watts capacity. However, circuit breakers are regulated to a capacity of 80%. 1800 total watts times 80% is 1440 allowed watts. Maximum wattage capacity should not exceed 1440 watts. There are newer breakers called arc fault breakers. These circuit breakers monitor the RF noise on the hot and neutral wires to detect unintended electrical arcs. However, these arc fault breakers are prone to nuisance tripping from any large, powerful, or high-performance electronic devices. These arc fault breakers are becoming more common due to code and regulation. They are required in bedrooms since 1999 due to U.S. electrical code, and required in all living areas since 2011 per NEC. Be aware of your local laws. They may change from country to country, state to state, and county to county. Arc fault breakers are only required to support up to 1,000 watts, instead of the 1,440 watt maximum with the other breakers. If a device requires more than 1440 or 1,000 watts allowed by the circuit breaker, a power booster can be installed in line. It uses the dimmer's output from the load wire as an input signal and controls the load using reverse or forward phase dimming. Power boosters can generally dim up to 16 amps depending on the load type and the voltage. They are readily available from electrical wholesalers and online, but they do require additional wiring and a location for the installation in line between the dimmer and the load. This concludes Module 1.